Let's start our week 3 lecture. It's very important, equilibrium and moments in 3D. So we will determine the unknown forces using equilibrium equation, using free body diagram of system in 2D and 3D. Okay? 3D portion is very, very important, and it will be in the exam 1, exam 2, and the final exam as well. Okay? So very important, pay attention. And then we'll review cross product of vectors, so vector product, briefly, to find the moment of force, so 3D moments, basically. So today we'll solve 3D equilibrium equation, and then we will calculate the 3D moment. So two things are very important thing. Okay, and then now let's start with the free body diagram. So you already know what is free body diagram. We already talked about the brief definition of free body diagram. So if the exam statement is given, then we must choose a point of interest and then plot the free body diagram, right? So, and then this is kind of systematic steps to plot the free body diagram. So first, isolate the body of interest to make free body. So something like this, right? Something like that, right? And then draw your axis system, Cartesian, X, Y, Z, rectangular or polar or path. But we will mainly use Cartesian. And then, so something like this. And then add in applied forces. So here we have this force, and then gravity. And replace support with forces because we remove this support to make a free body. So instead of this inclined surface, we added friction and the normal force. And then draw appropriate dimensions. So here, this is rigid body, so it doesn't have any dimension here per se, but it has an angle here of the inclined surface. So these are 5 steps to plot the free body diagram. And we will not plot the free body diagram today, but you will with your TA on Thursday on 2D and also 3D. Okay, then let's move on to 3D, and this is the review slide. We talked about this last week, right? So in 3D, we have 3 directions, right? So if this is force, and we have magnitude in X, Y, Z direction, and then those are here Fx, Fy, and Fz, and then we indicate the directions using the unit vector, I, J, K. Unit vector is where the length of the vector is 1 and indicating the direction, right, X, Y, Z, right? So then we talked about how we express the force vector with the magnitude and the directional vector. And then, so this is the magnitude, and then directional vector is found by this, right? And then the meaning of each component here within the parenthesis is here, theta x is, so theta x is inverse cosine. So cosine theta x is this, and then cosine theta y is this, so we can find these angles here, right? So then now, equilibrium equation in 3D. So in vector form, we have this one equation, sum of the force vectors equal to 0. So R vector, that is resultant, equals to summation, so sigma, or the force vector equals to 0, right? So with this vector, if it is 2D, we have 2 components, x, y, right? If it is 3D, we have 3 components, x, y, z. And we are talking about 3D, so we have 3 equilibrium equations, fx, fy, fn, z. In each direction, sum of all forces equal to 0. Okay. Then we'll solve this equation using the first problem today, later together. And then I'd like to share this 3-dimensional problem. So this is a tower virtual reality model created by one of you in last year as a product of outcome of final project. Okay, so first clicker quiz. So before starting, I'll explain the problem. So there's a hot air balloon here supported by 3 cables, AB, AC, and AD. If the resultant of these 3 cable tension is R minus 300J, right? So this direction. What is the force P exerted at A by the balloon? So you are solving this equilibrium equations. So sum of force, all the force should be 0, and then we have 1, 2, 3, and force, unknown force P, right? And then sum of these 3 vectors equals minus 300J. Then what should be P vector? And then we know equilibrium is sum of all the vector for force vectors 0, right? And what do you think? Is it 0 minus 300J the same, or 300J the opposite way, or 900J? Okay, I close after 10 seconds. Okay. And let's see the results. Yep, C has the most votes. Yeah, and 4, B, and then 2, D. Okay. Okay, so yeah, C is correct, right? Why? Because if the resultant force here, okay, here is, so the smart pen is not working, so I just use this. So sum of these 3 forces are minus 300J, so this direction, right? And if we have 300J upward, then sum of these 2 vectors, 0, right? So that's why this is correct, okay? Okay, so now we'll move on to the next learning objective, cross product. Okay. So it's review for those who already took the multivariable calculus. So cross product of 2 vectors P and Q is defined as vector V, which satisfy the following conditions. So line of action of V is perpendicular to plane containing P and Q. Magnitude of V is P times Q times sine theta, and theta is the angle between P and Q. And direction of V is obtained from the right-hand rule. Okay. So, and these are some properties. So cross products are not commutative. So if you change the order, we need to add minus, and it's distributive. So we can say the left-hand side and right-hand side are the same, right? And then this is not associative. So if you change the order of calculation, so P cross Q first or Q cross S first, the results are different. Okay. Okay. So and then this, if I, J, K are unit vectors of X, Y, Z, right? And then I cross I is 0, J cross J is 0, and K cross K is 0, right? Why I cross I equals to 0? Yes, because theta is 0 right here. This is 0, so how? Okay, and then I about cross product of each vector. So we are using this order, right? So I cross J is K. J cross K is I, K cross I is J, right? So as far as we are calculating cross product for this direction, it's positive. And if we use the opposite direction, we need to add minus. So I cross K is minus J. K cross J is minus I, something like that. So I cross J, this direction. Okay, so that's that. And then if we know 3 components of each force vector, then how can we calculate P cross Q? It's here, right? So this is the equation of conducting cross products, and then I will definitely give this equation to you for exam. And then graphically, you can use determinant method, right? So you are using 3 rows. First, ijk, and then second one is magnitude of the first vector, xyz component. And then third row is xyz component to the second force vector, right? And then, right, p, so this times this minus this times this, I, something like that, right? So this and then this are the same, yeah, result. Any questions? Okay, so I went through this very quickly to introduce you this moment, okay? So moment of a force about a point 2D. So what is moment? Moment? So moment is some kind of sensation to include rotation, okay? I don't know. So if there is a pivot point root, so moment should have always a reference point, some kind of pin or pivot point, and then on this object, there is a force induced, right? And then if I induce force this direction, and then it will move upward, but it will also rotate, right? This direction, right? So this kind of sensation is called moment. Same as torque, moment, right? And then to use this graphic, so if there's a plane and then a reference point O, then a force, right? And then moment about this point O is force times distance d, okay? Same as torque, right? And then about the sign, so in 2D, counterclockwise is positive and the clockwise is negative. So you can just remember in 2D, counterclockwise is positive, okay? Okay, so this is definition, and I show you some demo here. No, I cannot do this. Okay. Okay. Okay, so moment in 2D. So moment, you saw the moment equation, but moment is moment arm times force. So force magnitude, right? So magnitude times moment arm, and the moment arm is the shortest distance from the reference point to the line of action of force. So shortest distance from the point to the force. Okay, and then let's practice that. So there is a 300 force here is applied at A, this direction. Determine the moment of this force about D. So where is D? D is here, okay? Then, so let's just clicker 2. So what is the moment about this, of this force about D? So I start the clicker quiz. And then this is 200 millimeter, and then this is 100 millimeters, and the distance from D to this point is 224 millimeters. Okay, I close after 10 seconds. Okay, so we have 8 A's, 15 B's, and then 190 C's. Okay. And the answer is A. Why? Exactly. So moment arm is perpendicular distance from a point to the force, right? And then this is the force, okay? Then you need to think about the line of action. Line of action is here, right? And then perpendicular distance from here to this force is this distance, not this distance, okay? And I like this clicker quiz a lot because after this quiz, you know much better about this moment arm. So, and then let's try this again. So if the force is changing like this, okay? And then what is the moment of this force about D? So I also start the clicker and then choose from 200 or 100 or 224. Now perpendicular distance from the point to the force. Okay, this is the second one, so I close after 10 seconds. Okay, now we have majority of votes at B, and B is correct. Great job. Yes. Yeah. So that is moment in 2D. Okay, so always in 2D, force times perpendicular distance. So that is the moment. And then moment in 3D is a little bit tricky because we must use vectors. And therefore, we must use cross product. So I'll show you. So moment of 3D force vector F about O is defined as this. So moment about O. So we always indicate the reference point with moment, so as a subscript. So M sub O, that is a vector too. That is R cross F. I cross F. So R is the position vector, and then F is force. So F, you know everything, right? But R, it is first time, so first concept, right? It's new concept. So let's talk about this. So it is 3D space here. And then this is O, the origin or reference point here. And then we want to calculate M sub O. Okay. And then the force vector is here, 3D. So some force inducing some rotation of this sphere or this body in this direction, right? And then R is position vector, or is vector. So it's a vector connecting the reference point to the point of action. Okay. So I repeat, position vector is a vector connecting the reference point to the point of action of the force of our interest. Okay, if there's a force, and then this is point of application, right? And then this is the reference point, and then this is the position vector. Okay, so R is this vector. Okay, so moment is R cross F, R cross F. R is position vector, and F is force. And then the magnitude of M sub O is RF times sine theta, and theta is the angle between R and F. And sense of the moment may be determined by the right-hand rule, so something like this. So here, right-hand rule, right? So x, y, z was first vector. So something like this, first vector, and then second vector, and then this is the direction of moment, right? First, second, and we'll practice that shortly in a clicker quiz, okay? Okay, then I show you here to calculate this one. So if R is position vector and then the force is something like this, okay? Makes sense, this is reference point, and then this point of action of the force, okay? And then R cross F is moment. But this R is not the perpendicular distance, right? So this is a vector just connecting reference point to the point of action. It doesn't have to be perpendicular to the force, right? And we use M is R cross F, okay? Then if we extend this force vector here to find the perpendicular distance, and then this is perpendicular distance, right? So it's 90 degrees, right? And then R and D are not the same, right? And then if we say this angle is the angle between the position vector and the force, right? And then do you see the relationship between R and D using theta? Yes? What is that? Anyone who can share? Sine, yes. Sine theta, right, is R over D. And then indeed, R times sine theta is D, right? So we can write like this. So this is definition of cross product. So R times F times sine theta, right? And then R sine theta is D. So it's consistent with 2D definition, but it's 3D, so we must use 3D vectors because there are 3 directions, okay? So yes, summary of 3D moments, R cross F, if R is force vector, a 3D vector, and then F is 3D force vector, right? And you can use RF sine theta. If you can find the perpendicular distance, then you can also use DF, but in 3D, most likely you should use cross product, okay? Okay, good. And then clicker quiz. So, which is the correct direction of movement induced by this wrench? So here, this is practice to find the direction of the cross product. So I initiate, and then use your right hand, right? And then what is the position vector from the bolt to the force, right? So this is the position vector, and then force is this direction, right? And then use the right hand rule, and then which one? Which direction is the movement? Right direction, and this left or forward or backward. Yes. That's left. That's left, right? No, it will, like, so if you are unscrewing, right? Unscrewing, right? So rotation, so think about the rotation. How the bolt is rotating. Okay, I'll close after 10 seconds. Okay, so we have variety of choices. So here, C has the most votes, but we have some A, B, and D, okay? So let's figure that out together, right? So right hand, right? And then index finger is the first vector, and what is first vector? It's position vector, so this direction, right? And then the rest of the finger is the force, right? And then what is the directional force? Upward, right? So the answer is this direction, right? Forward, okay? So so if you didn't try with your finger, right hand, try. First vector is this position vector, this direction. And then force is this direction. So that's why the force should be, so moment direction should be this direction. But what does that mean by moment is forward you? This is the direction vector of moment, but moment is rotation, right? So, the meaning that the directional vector of moment is forward is that moment is this direction, okay? It's rotation, so counterclockwise to this direction. So, right? So there's a bolt, and then we are pushing this, right? So moment is this direction to unscrew this bolt. So today we have 3 problems. So first one is 3D equilibrium equation, and second one is cross product. And the third one is 3D movement, so very important, okay? And then we are recording this session, so if you miss anything, please use course recording afterward. And this is the first problem, so this is the same problem we solved last week to find the force vector, but we'll solve unknown force today. So a rectangle plate is supported by 3 cables as shown, 1, 2, 3. Knowing that the tension in cable AD is 520 Newton, so this magnitude is given, determine the weight of the plate. So the plate weight is W, and the weight is acting downward, so we know the weight, the W, right? But we need to find the weight of the plate, and also we can find the cable tension. Okay, so let's solve the equilibrium equation. And then, technically speaking, we must find all the cable tensions using finding coordinates, right? And then find the directional vectors, right? But because of the time, I added these 3 vectors here, so especially the directional vectors here, okay? So then, let's set up the equilibrium equation for this. So, before that, free body diagram. So we need the free body diagram first. So here, we have 1, 2, 3, 4 points, right? And then, or maybe 2, so 5 points. Which point should we use for the free body diagram? A? Any other opinion? O? Or BCD? No. Not BCD, okay. Then O or A? A. O is good point, but cables are not connected at O, right? So we cannot tackle the cables. So that's why A is good point, okay? So A is good point. Then now let's indicate 3 cable tensions, okay? So along these cables, so I'll add something like this. And then indicate AB, AC, and then AD. And then cable tension should be away from the node, so the direction of these forces should be downward pulling, right? Okay. And then we know the weight of the plate is here, and then this is always to the center of the earth. But we must find this force, right? It's supporting force, it's a force supporting the entire plate using all 3 cables, right? And then this force should be upward or downward based on the equilibrium. Upward, right? And then the magnitude should be W, right? So if we don't think about this 3D cable, 3 cables, right? And then W is downward, then a force acting on the ceiling to support this weight must be W. So these 2 are balancing out in equilibrium, in other words, right? So now this is the free body diagram. So we have 4 forces acting at A, and we want to find what W is and what other 2 cable tensions are, okay? So then, 3D equilibrium equation. So that is all the force, summation of all forces equals to 0, right? So this first vector equilibrium equation I show you. And then we have 1, 2, 3, 4 vectors. So we can vector sum those 4 forces, right? So TAB vector, and then TAC vector, TAD vector, and then this W vector equals to 0. So conceptually, it's okay. We are summing all 4 vectors, right, together, and then that must be 0 to make it equilibrium, right? Any questions so far? No? Okay. Then now, we need to find the 3D component of each force vector. So that is the next step. And then TAB, so this vector is magnitude times directional vector, right? And directional vector is, so using this, right? It's AB vector divided by the magnitude of AB. And then we are giving this one here. So please practice this one in one of the discussion section on Thursday with your TA. But you can find this one using last week's lecture. Okay. So, and then TAC is this. So this is given. And then TAD is also this, but TAD magnitude is given. So I write this is 520 Newton here. And then the last one. So W vector is unknown. So I use the magnitude as just W. And then what is the directional vector of this W? Upward. So J, yes. Unit vector of y-axis, J, right? So I use J. Okay. Any questions so far? So we set up the equivalent equation. We found vector components of these 4 vectors. And then the next one is substituting this one into this equation. Okay. So yep, let's write that down. So first one, TAB minus 8 over 17I minus 12 over 17J. So I'm just copying 9 over 17K. Okay. So, yep. And second one is TAC. So I'm copying this one here, the second. So TAC times 0.6I minus 0.64J plus 0.48K. Okay, follow me, right? And then the third vector here is 520 Newton times these. This is the directional vector. So 5 over 13I minus 9.6 over 13J minus 7.2 over 13K. Okay. So wrote down up to here. And then W vector is this. So plus WJ equals to 0. Okay. Any questions? Okay, yes. Okay, good. And then this is the vector equivalent equation. And then now we have I, J, K. So these indicate whether this term is X component, Y component, Z component, right? So we can set up each component equation. So for example, X component is in front of I, right? So let me use, this is in front of I, so X component, X component, X component, and then Y component, right? So I write that down. Minus 8 over 17 TAB, first one. And then second one, plus 0.6 TAC. And then the third one is this, right? So when I calculate this, 520 times 5 over 13, that is 200. So plus 200 equals to 0. So this is sigma fx equation. Okay, so this equation is sigma fx equation. It's only x components. Okay. And then you can write y and then z component from out of this equation, right? So I'll give you about 2 or 3 minutes. So let's write down y equation and then z equation from here. So y in front of j, 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 and j, right? And then z in front of k, right? So. Okay, so this is what I've got. So y component here, minus 12 over 17 times TAB. And the next one is minus 0.64 TAC. And then the third one is this times this. And then fourth one is W. Okay, plus W must be here. We must find W from this problem. And then Z component, this times TAB, this times TAC, and then this. So that's 288. Okay. Any questions? So these three are three scalar equations. And then the first equation is this vector equation, the same. Okay. And then now we have these three equations. So let's say this is 1, this is 2, and this is 3. And we have how many variables? TAB, TAC, and W, 3. So 3 equations, 3 variable, linear equations, we can solve it, right? So I would solve 1 and 3 first, because 1 and 3, it has only 2 variables, TAB and TAC, right? And then you can find TAB and TAC, and then substituting this number here and here to find W, okay? So you can use any method to solve the linear equation, but I recommend using calculator if you know how to use it. So I'm not related to TI, but my calculator is something like this, right? And then I use system solver here, and then 2 by 2 linear equations, and then I input the coefficient here. So first one is minus 8 over 17. And then second one, minus plus 0.6. And then it's 200, but on the left-hand side, so it should be right-hand side. So I use minus 200. And then number 3, here, 9 over 17. And then here, 0.48. And then this should be right-hand side, so 288. And then solve. Oops, yep. Something wrong? Okay, so I fixed my problem and then I got this. So TAB is 5,440 over 11. And then TAC here is 600 over 11. Right, and then if you calculate this, it's 494.5. And then this, 54.5 Newton. Yes? You are using a different calculator than mine. So if you can find some kind of system solver. Yes?
You have to go to apps, and then it's number 9, and it's simultaneous equation solver.
Oh, okay, thank you. So did you? Yeah, okay. TAs are helping too, but yeah, thank you. And every calculator has different function. So you can go to app and then system solver and use them. Okay, then so I mark here. So use your calculator. That is the tip. And then once you know TAB and TAC, you can find W from equation 2, and I'll give you W. Okay, any questions? Okay, good. Then we move on to the next problem here. So next problem is problem 3.20. And then determine the moment about the original of force here. So force is determined. So force is fixed. And then the position vector is different for each selection. So A is here, B is here, C is here. Yep. So maybe shock from calculator, so please pay attention back to the problem solving, okay? So this problem is cross product, right? And the force vector is given, and position vectors are changing, right? And then let's try 1 with everyone, and then 2 at home, and I'll give you the answer for the other 2. So which one do you want to solve with me, A, B, or C? Oh, okay. So let's try A. So it is. So for A, position vector R is 2i minus 3j plus 4k, and then F is 4i plus 10j plus 6k. Okay. Then moment about A, right? So that's R cross F, right? R cross F. So that's what we learned today. And then let's use the determinant method. So 3 rows, and first row is I, J, K. And the second row is R. Third row is F, right? So for A, this is R. So 2I minus 3J, and then 4K. And then F is the same here. So 4I, 10J, and then 6K. Right. So let's calculate this together. So first, I component. So let's use this divider here, and then this multiplying this minus multiplying this, right? So minus 3 times 6, minus 18, minus this times this, 4 times 10, 40. That's the I component. And minus J component, so divider here, right? And then these 2 minus this 2, right? 2 times 6, 12, minus 4 times 4, 16, J. And the last one, so using this divider, right? And then this 2 minus this 2. So 2 times 10, 20. 4 times minus 3, minus 12, and K. Okay. So then what is I component? Minus 58I. And then this one, so inside this minus 4, and then we have minus 4, plus 4. And then 20 minus 12, 20 plus 12, so 32. Okay, so this is the determinant method. Any questions? Okay, so this is A. Answer is this. So I'll give you answer for B and C. So B, 6I minus 4K. For C, minus 30I plus 12J. Okay, any questions? Yes? This one? That is the equation. Yeah. So good, very good question. Why this is minus? Yeah, it must be minus because I multiply. So I use this this minus this. We must use minus here. Yeah. Question.
Does it matter if we put the four vector on the top? Because it can assign the product. Does it matter if we put the four vector on the top instead of on the bottom?
Good question. Can we? Does it matter if we change the order? Force vector top and position vector bottom. Yes. So that is the property of the cross product. You change the order, then it's different. You will get negative value. Yeah. Then you can use. So you cannot use force in the. Force in the bottom. Yep. Always R cross F. So second row position vector R. Force third row. Yep. Good question. Okay, then the last one is 3D moment. Okay, so, wow, it's high. So you determine the moment about all of the cable tensions A, B, and BC, right? So there is a tree here, right? And then B is a point where cables are connected. Here, so cable AB is here. So pin at A, and then B is on the tree. And then BC cable is here too. So C is a pin, and then B is on a tree, right? And then obviously these cables are kind of pulling this tree, not make it fall, right? And then what is the moment about O? O is the origin here, so O should be here. O about of the cable tension AB and BC. So it has two cable tension here. And then there are A, B, and C. Then for the free body diagram, we must use B, right? So, and then at B, there's cable tension away from the node. So this direction. So T, B, A. And then the other cable tension, here's T, B, C. And then this is the origin, O. And then we need to find the moment about O of these two cable tension. Okay. Okay, then moment is R cross F, and then F is given. So what's R? R is a vector connecting O and the point of action, right? So this is R, right? So this is our so a vector connecting O and B. So OB vector is position vector in this case. And it's the same for both cable tensions, right? So then we have two forces. So we can write R cross TBA for the moment from the first cable tension, and so add plus R cross TBC. So that's what I can write. So there are two forces, and moment from each force is R cross F. So R cross F, and sum them up. Okay, and then R is this vector, so I'll add OB here as a subscript. So any questions? So this is the first time we applied the moment equation. So 3D moment equation here. So I'll repeat here. So moment about O of these two cable tension is using cross product R cos T, first one, and R cos the second cable tension, right? And then this R position vector is a vector connecting the reference point to the point of action of the force. So the first vector is here, point of action is here. So OB is position vector. And then for the second one, point of action is the same, right? So that's why OB is the position vector. Okay, so then R cross F and R cross F. Okay. Yep. And then we are all engineers and we learned math a lot. So do you see some rules here about the reference point? Reference point is O. And then in the position vector, the first subscript is always O. Yeah. Because the position vector is a vector connecting reference point to the point of action, right? So first reference point must be the first subscript here. And then what about the second subscript? Point of action of the force. So if you know the force vector, then the first one here is the second subscript here. Same thing. So that is how you quickly set up 3D moment equations. Okay. It's OB, OB. Okay. Any questions? Okay. Then now in the problem, TBA is given, TBC is given, and ROB is also given, so we can plug in and then calculate. But we see this ROB is repeated here. Can we use some of the properties of cross product? Yes. Distributed. Yes. So we can write this equation as this. And then it's easier to calculate, right? So sum of these two vectors and then this, and then calculate. So I write the first component is 7j, and then second component is this plus this, minus 45 plus 340. So I give you the numbers here. Sum of these two is 295i minus 960j plus 440k. And now, how can we calculate this? I think the best way is using your calculator, cross product. Second method is using determinant method, right? And then the third method is using the equations, right? So this is first time. So if you have calculator, please feel free to use it. And if you don't, yeah, let's use the determinant method together. So first row is ijk. Second row is 0, 7, 0. And then the third row is 925 minus 290, 440. Okay. And then for I component, we have 7 times 440 minus 0, so I. And then for J component, 0 minus 0, so 0. For K component, this is 0 minus 7 times 295, so minus 7 times 295k. So when you calculate this, and then this, it is 3080i minus 2065k. Okay, so this is the result. And then what is the unit of the moment? Is it given? Position is given here, meter, and maybe Newton meter. It looks like SI, so Newton meter is the unit. And then let's think about the physical meaning. So here, this is x-axis, y-axis, and z-axis. And then the component is here, 3080 I. So x direction about something like this, right? And then z direction minus 2065. So 2/3 of I, right? But in the negative direction, something like this. So this is the direction of the moment, right? Direction of the moment. And then, so this is the direction of moment. And then the moment should be this direction using the right-hand rule, okay? So please look at this direction. This moment, directional vector we calculated, right? And then this is the direction. And then as an engineer, please think about the direction of these two moments where this two cable tension is inducing on this tree. Is it this direction, pulling this in this direction? Or is this direction? If it is pulling? Yes, to me it looks fine because it is this direction, right? And then the second one, this direction, some of them, this direction, right? So that makes sense. And then 3D moment must be expressed as this vector perpendicular to the plane. Okay, that's why.